Good afternoon, friends. My name is Jonathan Allen. I'm a physicist and one who specialized in environmental stuff. I've spent most of my career in solar energy and renewable energy, and I've also done a fair amount of work on aerosol particle analysis. What I'm going to talk about is the history of how electronics, including computers, of course, have assisted us in analyzing and studying the environmental problems which now face the world, especially climate change and other forms of pollution. So, in order to solve our environmental problems, we must first measure and analyze them. Now, systematic meteorological records don't date back to the mid-19th century. Measurements then were made by purely mechanical instruments and or a trained eye. And chemical analysis was all done pretty much by wet chemistry, as we call it today. So, the traditional measurements that we have to make are temperature, barometric pressure, the wind vector, which means speed and direction, humidity, precipitation, and visibility, which is the reverse of light scattering. Those light scattering is what limits visibility. Now, in the 20th century, as electronics evolved, especially the development of reliable and well-performing vacuum tubes, mostly in the 1920s and 30s, but it continued long after that, electronic measurement became faster, more accurate, more sensitive, and did not require the trained eye and special skill that some earlier methods did. They also allowed remote measurements, data recording, data storage, and synchronization between multiple weather and monitoring stations. The computer age has further facilitated digital records, computer analysis, and also graphics and statistics. So let's look at the evolution of some of these electronic instruments. But first, we have to look at the traditional ones. Here is the mercury thermometer. We're all familiar with that. The mercury barometer, where you have atmospheric pressure against the surface of the mercury, a vacuum above, and the head, the pressure difference generated by that column of mercury, which nominally for full atmosphere is 760 millimeters, gives you the barometer reading, which changes slightly, and that's an indication of weather events. The anemometer and wind vane. The anemometer consists of these cups, which are on a low friction shaft. The concave side of the cup has a lot more drag than the convex side, and so it rotates. This side goes away from you, this side is coming toward you. The wind vane is the same as the weather vane has always been. Consists of a surface area that tracks downwind and a pointer which usually points upwind and also counterbalances the weight of the vane. The humidity was measured by what was called the sling psychrometer, or the wet and dry bulb thermometer. You have two thermometers here, classic mercury glass thermometers. This one, the dry bulb, measures the ambient air temperature. The wet bulb, the bulb is wrapped in a cotton sleeve, which is saturated with water. And when you swing it around, just as you swing a sling, the David type sling, the wind that's caused by its movement evaporates water from the sock and chills the wet bulb thermometer to a lower temperature. The lower the humidity, the greater the temperature drop. So from the dry bulb temperature and the delta T, you calculate the relative humidity. There are charts, slide rules, and of course, computer programs that will do this for you. The rainfall, and here's a standard collecting rain gauge. The cross-section area of this funnel is 10 times the cross-section area of this tube, or 3.16 times the diameter, square root of 10. So a tenth of an inch falling in the funnel gives you an inch on the tube, and from that you can calculate the total rainfall. And finally, visibility was measured by sighting remote objects, the known distance from the weather station. The furthest ones away you can see defines your visibility. Once again, a trained eye does come into play. So let's look at the evolution of electronics instruments. These began with improvements to or direct replacements of the traditional instruments. But as we invent new instruments, we are faced with a trade-off between improvement and continuity. Remember, whether meteorological records go back 150 or more years, you don't want a new instrument to behave so differently from the old one that there's doubt as to whether the records are continuous from one to the other. That's one of the reasons why modern anemometers still use the spinning cups, even though you can have things like hot wired instruments or pitot tubes, which don't have any moving parts. Temperature. Electronics made all this possible. And here's the tube display at the Sarnoff collection. I took a photo of that just so we could include it. Measuring temperature. Shit, what happened here? There's this graph did not show. There's something wrong because it was on the okay, well, basically it shows resistance curves of metals versus temperature. Characteristic of most metals is that their electrical resistance increases with rising temperature, and you have and it turns out that while platinum does not have the steepest curve, the highest temperature coefficient of resistance is extremely linear, which in the days before computer programs which could correct nonlinearities, it came to be the standard metal for the thermometers. And here we do have, what's on here? Oh, here we have a platinum resistance thermometer. You have a coil of platinum wire in here, very thin wire. It's inside a protective sheath, which is usually hermetically sealed. There are wires coming out the end, often full wires, so you can correct for any stray resistance in the leads. And the standard instrument is known as a PT100 because its resistance is 100 ohms at 0 degrees C. And that is taken as the instrument. It has an electrical output, so you can transmit the data, store it, and do anything you want with it once you have a reading. Now, atmospheric pressure. We use now what's called a capacitive barometer. Is the dominant kind. It's the dominant brand is Baratron, made by the MKS Instrument Company. I believe they used to be located on Route 128 near Boston. I think they may still be there now. But anyway, the way it works is you have a diaphragm made of a thin sheet of metal, which is sealed. Above it, excuse me, the space above it is open to atmospheric pressure. The space below is a vacuum. And as the atmospheric pressure increases, the diaphragm bulges downward, and the capacitance between this grounded plate of the capacitor and the live, a hot plate of the capacitor, becomes greater. And this, you feed it to a capacitance meter, and that gives you your barometric pressure. Once again, the output is electrical, so you can send it to wherever you wish. Now, the classic anemometer for measuring wind speed usually used reduction gears and a stopwatch to count revolutions per minute, and that gives you that, and the constant relating RPM to wind speed allows you to get wind speed. The modern device uses what's called an optical tachometer. The optical tachometer has a disc with slots around the perimeter, a light source here, which can be an LED, a regular bulb, anything you want, and downstream you have a photosensor, and as the slots pass through the light beam, it blinks on and off, and the frequency of that is what gives you your RPM, and hence your wind speed. Wind direction, very similar trick. You have here a called a rotary optical encoder, and it's got slots in it. The black areas are the slots. As you move out from the center, each concentric track has twice the number of slots as the preceding one. So the result with these detectors that pick up the light from these sources gives you a digital reading, right straight to digital. Good for you computer jocks. And that gives you the azimuth, the wind direction. Yes?
Is it, forgive me, but does it really use a binary, or why does it use a gray code?
I suppose it could use a gray code too.
Because there's a lot of ambiguity.
Oh yeah, maybe they do. I don't know. I'm not sure. I'm not.
Okay.
I'm
sorry.
It could very well be a gray code. Both would work, I suppose, but you're right. With the gray code, you're not flipping two digits at once. Is that what bothers you?
Yeah, exactly.
Yeah, it may very well be so. The way, if you look at the detailed picture of this,
It shows a binary code.
yeah, it says Bruce, resolution bit type binary code.
Yeah.
I suppose a gray code might be better. You're right. But anyway, that's the brand we're stuck with.
Sorry about that.
No, thank you. That's something I hadn't thought of. Humidity. Dew point measurements have replaced most wet dry bulb thermometers. Dew point is a temperature at which atmospheric moisture will just begin to condense on a chilled surface as a fine dew. And as with wet dry bulb, the air temperature and delta T allow you to calculate the relative humidity. Different charts though for the two phenomena. Early dew point measurements instruments were very awkward and expensive and complicated. For instance, they either used open evaporation of a volatile liquid such as ether to accomplish your chill, or they would use a vapor cycle mechanical refrigerator. And once again, they required a trained eye to see just when that dew was starting to form. The modern instrument, however, uses a completely automatic system. A collimated light beam strikes a mirror, which is actually silvering on top of a copper block. The light reflects off it, and if there's no dew, you get the full intensity of the beam striking an optical detector. The output of the optical detector goes to a basically a thermostat. So the more light strikes this, the less power goes to the heat pump, which is a Peltier effect semiconductor device. No moving parts and cheap and easy. So as soon as you start forming dew, you lose some of the brightness on the optical detector, and the cooling effect is reduced, and eventually you hit an equilibrium. A thermometer in the copper block copper keeps temperature constant throughout, and that gives you your dew point temperature. Rainfall, the answer is fairly simple. It's a rain gauge with a tipping bucket. You've got this little bucket, which is on a seesaw-like structure, and the rain comes down the funnel, fills this up, and it flips down. This side flips up and starts filling up, and it cycles back and forth and back and forth. And every cycle, this magnet passes the reed switch and gives you an electrical signal. So the total number of counts gives you the total rainfall, and the frequency gives you the rate of rainfall, which is something you don't get very conveniently with your collecting type rain gauge. Visibility, we really do depart from the old time. By convention, you have a light source which shines a collimated beam of light at a 40-degree angle. Actually, the combination of this 20 degree, you got a 40-degree scattering angle, and the scattered light then it goes to a light detector. When there is no aerosols, the beam just goes right on through, and nothing goes to the receiver. As aerosol density increases, more of the light scatters, hits the receiver, and this gives you a number which you can relate to your visibility. So that's a similar instrument to that is going to come up in a little while for other purposes. So this is just replacements for the old-fashioned method. Now we're going to get into uniquely electronic instruments. The first of those is called spherics, which is a short form of atmospherics, and it came about in the late 1920s, early 30s for tracking lightning. The electromagnetic RF radio emissions from lightning had been documented as early as the 1890s, but it wasn't until the 1930s with vacuum tubes and indicating cathode ray tubes that we began triangulating on RF emissions from lightning. Now, conventional radio direction finding employs a loop antenna. And here you have one or more turns of wire inside a metal shield, which has a gap in it so it doesn't magnetically short circuit the field. The shield blocks the shield blocks the electric field, but the magnetic field induces currents. The changing magnetic field induces currents into this loop of wire, which then can go to a receiver. Great invention for homing in on a radio station, which is putting out a continuous signal. But lightning ain't a continuous signal; it's just a flash. So we got to do another trick. Yes. But lightning. Boom. The way a loop works, as I say, the signal propagates in its direction, and if the loop is edgewise on, the magnetic field, of course, which is perpendicular to the direction of propagation, induces current into the loop. If the loop is face to the signal, it's kind of counterintuitive, you get a null. And when you do direction find, you usually tune to the null because it's easier to detect with accuracy than the maximum, which is kind of sloppy. It's a sinusoidal function, basically. So the answer is crossed loop antennas. Two crossed loop antennas, and they're perpendicular to each other. The idea is that when you have the instantaneous flash of light, it induces current into both of these, and the ratio adds up as a vector, and you see over here your cross loops. They go into a cathode ray tube. The east-west goes into the horizontal plates of the electrostatic field, electrostatic tube. The north-south goes to the vertical, and you get a line across the face of the tube, which corresponds to the vector direction from which the lightning is coming. You also may, if you wish, include a sense antenna, which will discriminate out the 180-degree ambiguity. But if you go to triangulate, that's not necessary. So this gives you instantaneous flash direction. Now, if you have two, each of these is obviously a radio receiver, and it's tuned to a frequency below the broadcast band, usually around 200, 250 kilohertz. It's a long wave receiver, they call it, because that's where most of the activity of lightning is concentrated. If you have two such stations or more, and they're located some kilometers apart, it's possible to triangulate on the location of the discharge. And this is still in use. The modern version is known as the ALDF, Advanced Lightning Direction Finder Network. And in the United States, it consists of 130 sensor stations, and each one can detect cloud-to-ground strikes with a range of 100 kilometers or so. The next electronical invention is the radio sonde, and it also matured in the 30s. A compact radio transmitter is attached to a balloon. It transmits atmospheric pressure, which, as the balloon goes up, in fact, gives you altitude, temperature, and humidity. Humidity is determined here by a salt deposit on a glass plate, and the more humidity, the more conductive it becomes, and it gives you your indication of relative humidity. Today, we can include additional measurements such as chemical pollution and location with here we are launching the radio sonde. You've got your balloon, and below it is a parachute, such that when the balloon finally reaches the altitude at which it pops, the parachute allows us to descend gently to the ground. There's a tag on there that tells people who find it to please turn it into the weather service. In the United States, they often use helium for the balloon. In more resource responsible countries, they use hydrogen because helium is a very scarce resource. And here we have the box. Here you have a GPS receiver, so that it sends back not only its altitude, but also its latitude and longitude of where it is in space. You have a pressure sensor, which gives you your altitude. There is the antenna. Looking at the length of this, it's clearly working in the UHF. You have a temperature sensor and a humidity sensor. The earlier radio sondes worked in the HF and VHF. They had a longer antenna wire trailing down behind them. Now the next device is radar. Radar is an acronym for radio direction and ranging. Radar, a microwave radar, which is the kind almost universally used now, began its use early in the Second World War, 1939 or so, and was used mainly for detecting enemy aircraft and ships. Radar it was vitally important, obviously, in the Battle of Britain and also in some of the naval battles, which took place in the Pacific, often in cloudy weather. Imagine a gunfight where you can see me and I can't see you. Mm-hmm. And the Battle of Leyte Gulf, the Japanese took quite a whooping because of radar. Anyway, radar operators, however, also observed a strange phenomenon, which was the backscatter of microwaves from raindrops. Now, for their purposes, it was a nuisance, but after the war, meteorologists started to exploit this in order to detect storms. Basic principle of radar: you send out, you have a very directional antenna, usually a parabolic dish. And this beam is shown much wider than any radar beam really would be, but for the sake of the illustration, that's what the way they did it. You send out a short pulse of microwaves, it travels through space, hits the target, and some of it reflects back. And the aim of the antenna gives you the azimuth, and the time of flight out and back gives you the range. And here are the formulas. The range equals time times the speed of light, which is 3 times 10 to the 8th meters per second. Nice, easy number to remember. Almost exactly 3, by the way. 2998 something or other, but it's 3. And divided by 2 because it's a round trip. Wavelength is c, speed of light, over f, frequency. Frequency is c divided by lambda, which is the wavelength. Beam width is determined by the diffraction limit, which is theta. Beam width in the angular beam width in radians is lambda over d, which is d the diameter of the antenna, or 50. And remember, a radian is about 57 degrees. So you got that done. The next improvement in radar is Doppler. As you know, when a source of a signal is advancing toward you, the pitch is effectively raised, the frequency is effectively raised. When it's retreating from you, the frequency essentially drops. So here you have your radar antenna looking at a cyclonic storm, and we're in the northern hemisphere, so it goes counterclockwise. When you're aiming at the advancing part, the frequency that comes back to you is 1 plus V over C times F naught, which is the frequency you sent out. The retreating part is 1 minus V over C times F naught. And from this, you can get the speed of rotation of the storm, identify it as rotating. And if the up and the down are at an absolute value equal, the storm is a constant distance. You can also tell whether the storm as a whole is advancing or receding. Now, getting down to what's of increasing importance today, and that's pollution. With rising concern over environmental quality, we've added measurements related to contamination and pollution, both gaseous and particulate. One of the gases which was attracting a lot of attention is carbon dioxide, CO2. And this was originally measured by drawing a measured volume of air through a chemical CO2 absorber as one of the carbonate salts. And you draw a known amount of air through, you measure the weight gain of the absorber, and that tells you how much CO2 is eaten up. Yeah, and hence the concentration of CO2 in the air. We now measure with what's called an NDIR cell, non-dispersive infrared cell. Non-dispersive means you're not using prisms and gratings as in a actual spectrometer. And you exploit some of the same wavelengths that CO2 absorbs, which cause it to enhance the greenhouse effect. You're catching it by its own trick. And here we have a CO2. There's something with the graphs, they're not appearing here. Here's a CO2 sensing cell. I don't know what's with this computer, but that particular format apparently will not. Anyway, it has a bunch of lines and it shows you what the wavelengths are. Anyway, here's a CO2 absorption sensing, CO2 sensing cell. And what you have is an infrared light source, which can be fairly broadband. An excellent one is a tungsten lamp, which puts out a lot of infrared. You don't even have to run the filament full voltage. And here you have 2 detectors with filters. One is the reference detector, which is tuned to a wavelength outside the absorption band, and the absorption detector, which is tuned right to the middle of the absorption band. When there's no CO2, these both pick up the same intensity because there's nothing in here that's eating it up. But as you add CO2, the absorption detector gets a weaker and weaker signal while the reference detector stays the same. And that difference allows you to calculate the amount of CO2 you got in the air. And a typical, by convention, we do try to set standards for these things. The conventional length is 40 centimeters distance. And Now, by the way, the official CO2 sensing cell, well, but when they tell you the atmospheric CO2 is now 30 or 40, I mean, 430, 440 parts per million, that's located at Mauna Kea Mountain on the island of Hawaii, because it's way up in the air. There are no industrial sources near it. There are no agricultural sources near it. There are no forests near it that would suck CO2 out of the air. And that's your official global CO2 reading. Now, another gas of interest is nitrogen oxides. NO, which is nitric oxide, and NO2, which is nitrogen dioxide. And they're both sort of uglies. They cause, and I'll get into that in a minute. Most measurements, they take the NO2, which is less stable, and they convert it catalytically to NO, and they call the mixture, the combination, NOx, because NO1 and NO2 mix together. There are two methods. One is very similar to the NDIR, but it uses 5.3 microns wavelength instead of 4.2 micron wavelength. They have different absorption bands for the different gases. But there's also one called chemiluminescence, chemical luminescence emission of light. If you mix NO with ozone, they react and they produce light at the near the upper end, near the blue end of the visible spectrum. And here we have the instrument. The instrument was patented right nearby at Princeton Junction at a company called Aerochem Research Labs, which is the first place I worked after I finished my PhD. And we at that time we were doing quite a bit of environmental stuff. So it was a friend of mine named Herman Voltrauer, whose name appears on that patent, and he was the one who developed it a little bit before I started with the company. Anyway, what happens here is you suck in air, or actually the exhaust draws in air. It passes through an ozone generator where you have a high voltage plasma discharge, and that converts the O2 to O3. It rearranges the oxygen atoms into the more unstable reactive form known as O3 or ozone, and it flows into the reaction chamber. Similarly, your air sample, which consists of NO2, converts to NO, and the NOx flows through a valve also into the reaction chamber. Now there's an excess of ozone, so that you don't run out of ozone. No, you don't run out of ozone, but you do use up all the NOx. And down at the bottom here, we see a photodetector, which is generally a photomultiplier tube, which is the most sensitive light, still the most sensitive light detector you can get. If you chill it down to dry ice temperatures to eliminate thermal agitation, it will count individual photons. Really will. Anyway, an interesting point on this instrument is it will also go the other way around. If you put in an excess of nitric oxide, and then you feed in ozone, you're going to measure the ozone, because that's the stuff that gets fully used up. And so it's a double whammy instrument. Yes.
I got this right, ozone and nitrogen oxide combine somehow?
Yes, they react and they produce. I think the ozone reduces to oxygen, and the NO.
NO2.
Yeah, and NO may go to NO2. Yeah, yeah. I think that's probably what the reaction that happens. But the point is that what? It releases photons of light because there's a drop in electron energy levels. So ozone is also a gas of some interest. It's both a good guy and a bad guy. In the upper atmosphere, in the stratosphere, it's a good guy because it absorbs and blocks the hard UVC light, which if it can penetrated down through the atmosphere, would be harmful to living things. But in the troposphere, it turns out to be a bad guy. It's a lung irritant. And it helps in the formation chemical reactions that form smog. So it's something we want to monitor and control. If you want to measure the total ozone in a column above where you're standing, you use an instrument known as the Dobson spectrophotometer. And the Dobson spectrophotometer, you have sunlight come in, you split the sunlight into two wavelengths, one that's absorbed, one that's not absorbed by ozone, and by the ratio of the two, which is analyzed by this optical system, you can determine how much ozone cumulatively is between you and the top of the atmosphere. Now, you can detect local ozone, as I said, also by using an optical absorption cell similar to the one for CO2, except here you're going to use UV light. Aerosols are small particles suspended in the atmosphere. As a particle gets bigger, its mass increases as a cube of its diameter. Its cross-section increase only as a square of its diameter. So as particles get smaller, they tend to remain suspended in the air for longer periods of time. And particles in the submicron range might take a day, or it may take hours to fall from here to the floor. And with a little bit of updraft, they can stay up indefinitely, pretty much. The original method of collecting aerosols is with a filter. Here you have a glass tube leading down to the filter, which carries one of these circular filter discs. They're made by the Millipore company, and you can get them in various grades for different aerosol sizes. And this pump that draws the air may look familiar to you. It's a compressor out of a junk refrigerator. I didn't have much money at the time to build a fancy compressor, so I just went to the junkyard and got this, and it worked perfectly well. You've got a vacuum gauge here, which tells you what the pressure drop is, and from this you can calculate the amount of air passing through, and you can analyze the sample by microscopy or chemical analysis or anything you want. The modern method, though, is to examine bulk aerosols by a turbidimeter, which is very similar to the instrument we looked at to measure visibility of the atmosphere. Just the light gets scattered from the collective aerosols. You can also count individual aerosol particles. And here's an individual aerosol particle counter. You take a laser, often a Heaney laser, focus it down to a very thin beam. You have the aerosol sample is drawn in, and the particles focus into a narrow stream. They pass through the beam, and if there are no particles in between, when there's no particle, the light just goes over here and gets absorbed in a absorption cell. Just a little cone painted black on the inside. The photons go in there and they get eaten up. Nothing comes back out. On the other hand, if there's a particle, it scatters the light, and it gets focused by these lenses and ends up at a photodetector. And the amplitude of the spike that you get from each particle, that is what determines the particle size, according to the Rayleigh or Mie scattering theorems, which are rather, which we can get into it. You guys can look that up if you want. I got my fill of it when I was doing my thesis. But you can also go beyond just counting how many particles there are. You can discriminate between spherical particles and irregular particles like crystals. And here is the shape-sensitive aerosol counter that I built. Inside this box is a Heaney laser, the one mirror is at this end, the other mirror is at that end, and it does not emit any net. It does not have a partially silvered mirror that allows some of the light to get out. It just goes back and forth in. So just as in a resonant circuit, the circulating light is much stronger than the light that you could squeeze out of the end. So you get a very intense light concentration, and so you can scatter. You can sense much smaller particles. On each side is a photomultiplier tube, one on this side and one on this side. And here's an exploded view. And by the way, this did not require computer analysis to make this, to doctor this photo. Just in the old-fashioned way, 5 by 7 inch negative, pencil, and all that kind of stuff. This line here is India ink, which in a negative converts to a, now, the output of these two photomultiplier tubes go to two amplifiers. One is a summing amplifier, and the other is a difference amplifier. The sum gives you the particle size, just as with the other particle counter, but the difference indicates asphericity of the particle as it tumbles through the focus of this beam. And that can be quite important because it can tell you whether a salt is in the form of solution droplets or a crystal. And it can also help you and if you know the humidity, it can help you to identify which of a group of particles you're examining at a time. So you get a spectrum of size and also that. We can even go one step further. And this is something we worked that I was a principal investigator on at Aerochem Research Labs. They're no longer in business, by the way. If somebody's interested later, I'll tell you what happened to it. But anyway, this is known as CART, C-A-R-T, which stands for Chemical Analysis of Aerosols in Real Time. But we called it the TIB, the thing in the barn, because the building in which we built it was a barn. Which, anyway, what happens is, once again, your aerosol stream comes in here, and it gets focused. It hits a vaporizer ionizer cell, goes to a mass spectrometer, and the mass spectrometer gives you, by mass spectrometry, a chemical analysis of what each individual droplet is made of, each individual particle is made of. So most of our measurements here, you've been at the site of the sample you're looking at. But what about remote sensing? Because it's sometimes not feasible to install an instrument at the point of measurement, nor is it practical to map a variable over a large area of tens or hundreds of square kilometers. Are we running short on time here? Or?
15 more minutes.
How much?
15 more minutes.
15 more minutes. Okay, we're in good shape. Thank you. Now, remote sensing can be either passive or active. Passive sensing, your sensing instrument does not emit any kind of radiation. It just senses what's out in the atmosphere, say coming from the sun or coming from the source itself. Active means you're emitting a ray of light, which can be visible, infrared, or ultraviolet. And that often takes the form of LIDAR. LIDAR is the light version of radar, not light in the sense of not very heavy, but optical light version of radar. Once again, you can send out a pulse, time it's out and back distance and all that kind of stuff. By the way, LIDAR is one of the methods that they're using now to navigate driverless vehicles. So for instance, if there's a railroad tie lying on the across the road, they can hit it with both front wheels simultaneously and flip the car all the way over rather than just roll it on its side. Anyway, so let me see what I was going to say. Remote sensing is often done from aircraft, and the earliest remote sensing was aerial cameras. They can map vegetation, wildfires and their damage, flooding, and also spot sometimes wildlife, and they can map temperature, gas concentration, and other variables. The aircraft can be a piloted airplane or a drone. But if it's a single engine airplane with the engine in front of you, you want to make sure that if you're measuring CO2 and that kind of thing, you're not sniffing your own exhaust, because that can be a little embarrassing. Gee, I wonder where all CO2 came from. Yeah. I'm going to get into the methods a little bit more, but when I get into more of it. Satellites. Satellite methods are in principle similar to airborne, except you're much higher up, hundreds of kilometers typically. And this allows large area coverage, but in some cases is going to preclude LiDAR because the distances are so great. Here in New Jersey, the RCA Astro Electronics Products Division built the television infrared observation satellite, Tyros-1, the first weather satellite in 1960, and put it up in orbit. And here she is. And these antennas send the radio signal back to the ground, and these are photovoltaic cells that keep the machine running. Modern satellites transmit data to ground on mostly by microwave. You can see these antennas, if you look at the length of them, are probably VHF, UHF. Now, polar orbits allow full global coverage because they're orbiting pole to pole, and the Earth rotates under the orbit, and over time they can cover the whole world. There are also geosynchronous and geostationary satellites, where the orbital plane is close to the equator. The difference is geosynchronous means that the orbital period matches the Earth's rotation period. Geostationary means that they're over the equator, but if the plane of the is a little off the equator, while the longitude is conserved, the latitude can fluctuate a bit. Geostationary means right over the equator, the spot that they're above is fixed for good. That has the advantage of being fixed for good over a spot, but also doesn't cover as much width. Okay. But we have to remember the geosynchronous orbit is way out there, about 36,000 kilometers altitude above the ground. That's way up. So LiDAR is absolutely ruled out, and only passive measurements are possible. Temperature measurements, any surface above 0 Kelvin emits thermal radiation. Let's see if this graph comes through. Yes, no. Oh, here's a Stefan Boltzmann equation. And the amount of power per unit area emitted. Let's do a little demonstration here. This is a tungsten filament inside a vacuum. And as you raise the temperature, you can see it gets brighter and brighter. Very bright, less bright, but also notice the color. The temperature is dropping, it turns redder and redder and redder and redder. And pretty soon, you can't see it anymore. But we're in the infrared. No visible light, but this is still eating up power. So that's the demonstration of that. So the Stefan Boltzmann equation says the power per unit area is the Stefan Boltzmann constant, which is 6.67 10 to the minus 8th, times the emissivity. That's how black the medium is. The tungsten filament is pretty close to 100%, times the temperature, absolute temperature, of course, to the 4th. So even if the emissivity has a small uncertainty, the very rapid rise of emissivity due to temperature can somewhat compensate for that. And now we have, finally a graph that came through. This is black body radiation versus temperature. The Earth's surface is around 300 Kelvin. And you can see that it's a moderately high curve. As you get up to 500 Kelvin, you're getting not only more intense, but you're shifting to shorter wavelengths. 3000 Kelvin is the temperature of a typical tungsten lamp filament. And the peak is just about at the red end of the visible spectrum. You can see the spectrum over here. When you get up to 5,770, 5,770 Kelvin, you're at sunlight, and the sunlight peaks right at the blue end of the spectrum and is even more intense. All right, that's this displacement of the peak is called the Wien's displacement law. So lenses, by the way, in the deep infrared, lenses and filters have to be made of things other than glass, because glass is opaque when you get down to below about 2 microns. So they have to use sapphire or quartz. And sapphire is not expensive anymore. They grow it synthetically, good quality stuff. But anyway, satellite thermal imaging can locate weather fronts, monitor the El Nino Southern Oscillation, determine the strength of tropical cyclones, and study urban heat islands and monitor the global climate. It can also spot wildfires, volcanoes, and industrial hotspots. And the beauty of that is that it can all be done from up in space, where you can have a wide field of view if necessary. Radiometric thermometer does work somewhat better over the ocean surfaces, where the emissivity is better known, is better quantified than over land, where there are still some small variations. And here we have the Earth observation satellite, which is currently in use, and you can see that in this drawing they've doctored it to show the track that is following. Methane is another gas you want to look for. By the way, of course, airborne satellites can track CO2 both by LiDAR and by reflected sunlight. Once again, a wavelength in the peak, a wavelength just outside of the peak. Another gas of interest is methane. It's also a greenhouse gas, about dozens of times as absorbent as CO2, but fortunately it does break down over time in the atmosphere. CO2 does not. It exploits IR light, but it's in sort of different bands. Hey, another graph came through. And as you can see, there are some absorption bands here. This is one near about 3.4 microns is a really big one, and that's the one you often want to use. And with satellite imaging and computer enhancement, we can actually create a map. Here is a satellite view of and this has been somewhat doctored with a pen to show the pipeline and all that, and the methane is encoded in red, so you can see where it is. And this is a natural gas pipeline full of methane, and it's leaking. Where is it? Texas! Big surprise. We can also detect more dispersed sources, such as anaerobic decay of organic matter in what we used to call dumps, and which we now call landfills. And also methane from cattle herds due to their farts and to their decaying manure. Once again, you might find some in Texas. Now, if we combine a lot of these techniques and use computer enhancement and graphics, we now have a computer-aided satellite map of CO2. And you've got a scale here that shows concentration. Red is the richest, blue is the Middle East, and you can see that the red tends to be concentrated over the regions of the world where the most industry exists. Once again, no big surprise. So electronics and optics have given us the means to observe and track the effects of pollution and climate change. Now what we need is a global will to mitigate these problems. And that is the end of the story. At least we hope it's not really the end of the story. Okay,